This is Dr. N. Ramya, Assistant Professor from Civil Engineering Department. Today, my lecture is on difference between laminar and turbulent flows. In last class, we have gone through the laminar and turbulent flows, right? So here we are differentiating what are the main factors that we are seeing now. So here, laminar flows, right? Laminar and turbulent flows. As we discussed, the laminar flows are flows which all the particles in a fluid are moving in a straight line. All the particles are moving in a straight lines, are in a streamlines, are in a well-defined path, are in a layers form. Laminars in laminars, we see the laminar flows in a layers in which are parallel to each other. So this is a laminar flow. And here is a turbulent flow. Turbulent flow means the fluid particles are not moving in a straight line. The particles are moving in a zigzag manner because it is not a well-defined path. It is a disturbance flow. The particles are not moving in a straight line, but here the particles are jumping from one point to the other point. One point to the other point. Like we are seeing difference, like zigzag manner of type of flows, like not in a straight path. It is undefined path. It is moving in a irregular paths. Is a turbulent flows. What are the parameters are making a flow in a zigzag manner? How the particles are moving in a straight line in laminar flow? Let us say this is a turbulent flows. So here, main factor, the differentiating factor for laminar and turbulent flows, the main first factor, the differential factor is a Reynolds number. So Reynolds number is coming into picture. Reynolds number, when the Reynolds number is less than 2000, is the flow we are seeing as a layers form, that is a laminar flow. But here coming to a turbulent flow, the Reynolds number is greater than 4000, then it is less than 2000. Here it is so here Reynolds number greater than 4000 is a turbulent flows. Here it is 2000. In between the 2000 to 4000 is the flow we are calling as a transition flow. Transition flow. So the worst factor, the differential factor for this laminar and turbulent flow is Reynolds number. Right? So Reynolds number. In Reynolds number, we are seeing factors. What are the factors contributing to the Reynolds number? That is density, velocity, and the diameter of the pipe which the fluid is flowing, and the viscosity of the fluid. So these are the factors are contributing the Reynolds number. Right. So here we said that the laminar flow, is moving in a very smooth, in a very ordered way, in parallel paths, parallel layers of fluid, and that particles are not mixing. Particles are not mixed. It is moving in a very well defined paths. Right. Here in turbulent flows, the flow is very zigzag, sudden changes, irregular motion with eddies and vortices. When the particle moving from one place to other place, due to this, there is a formation of eddies or vortices. Main factor of these turbulent flow in a zigzag manner is because of high velocity. First factor contributing to the turbulent flow is high velocity and having low viscous nature. Low viscous nature of the fluid, right? If the fluid is moving with very high velocity, then there is a formation or there is a transfer of particles in a zigzag manner. That means particles are jumping due to the high velocities. The particles are jumping from one to another place to zigzag manner. So these, when the particles are moving in this way, then we are saying that there are some eddies and vortices in the flow. Eddies means there is a vacuum, there is errors in the flow, right? Vacuum or air in the flow, that we are calling as eddies. Right. So here turbulent flows. Here in this laminar, the flow is, the velocity is low. The velocity is low, and the nature of the fluid is high. The viscous nature, the viscosity of the fluid is very high, so that the particles are moving in a very definite paths, in a well-defined paths. So main second factor is a velocity, right? So the velocity, if there is a change, if there is a high velocity with low viscous nature, then we see the flow is like turbulent. Means there we see some eddies, right? Here in this laminar flow, in this laminar flow, if the velocity is low and the nature of the fluid is very high, then that flow we see as a well-defined path, that is nothing but our laminar flows. So here the Reynolds number. So Reynolds number uh, main formula is the ratio of the inertia force to the viscous force. The ratio of inertia force to the viscous force is called as a Reynolds number, and it is a non-dimensional unit. And here the Reynolds number main factors which are contributing to calculate the Reynolds number are density, velocity, and characteristic strength by viscosity. Right? So that is your rho v d by mu. So these factors are contributing to calculate the Reynolds number. So here the Reynolds number rho v d by mu, as we discussed. So velocity, characteristics, dimension, and density. Right? These are all, and viscosity also. If these factors are contributing to the Reynolds number. Right? So here we are seeing a laminar flow. So laminar flow means what? All the particles, see here, as we are seeing in this image, right? The particles are moving in a very well defined paths, because due to the high viscous nature, high viscous, and the flow is moving with a low velocity, right? Low velocity. And here the turbulences, see how the particles are moving from up to here. So this at the eddies forming, right? So this is the flow, turbulent flow with high velocity and having the viscous nature is low, right? The Reynolds number less than 2000, it is laminar flow. Reynolds number is greater than 4000, it is turbulent flow. The Reynolds number 2000 to 4000, in between these, we call this as a transition state. We call this as a transition state, right? So here I'm drawing, this is the laminar flow, this laminar flow is changing, and here we are seeing the flowing as like this, right? Here we are say small disturbances in the flow. So this we are calling as a transition state. The where the flow is changing from laminar to turbulent flow. It is very a small distance, very negligible distance, very small. The distance, the conversion of laminar turbulent is very small distance, and it is very complex. It is very complex to calculate the transition distance, right? Transition state. It is very small, the conversion, right? So this is laminar and here is a turbulent nature. It is very complex to find out the transition state, right? Transition state. See, this is a laminar flow and here is a turbulent flow. There we are seeing some disturbances in the flow, and when we are seeing here all the particles are moving in a very well-defined paths. So due to these well-defined paths, the flow is very transparent, right? It is very transparent. So see, we are seeing clearly that all the particles in this are very moving in very well defined paths and in particular streamlines, a particular path with respect to the laminars like layers, right? So this is your transparent nature in laminar flow. Here we are seeing complete disturbance flow in turbulent flows. So here we are differentiating the laminar and turbulent. So here the in laminar flow the characteristics length are very characteristic of the laminar flow. So here in these we are seeing streamlines are parallel and it is moving in a very smooth motion, right? And fluid moves in a layers without disturbing the other layer. All the particles are moving in their own path with respect to the path. So here, as we discussed, low velocity and having the high viscous nature of the fluid, and one more thing here, the small diameter pipes favor the laminar flow. Here, the energy loss. Coming to the energy loss. So here, all the particles are moving in their own path. So the disturbances is very less. That's why the energy loss is also very less. Energy loss is also very less when comparing with the turbulent flows. And the example of these laminar flows are flow of honey and blood in capillaries. These are the examples of laminar flow, that is flow of honey and blood in capillaries. And here characteristics of turbulent flows. So here the differentiating the turbulent flow now. So the flow in a circular pipe is a random and it is an erratic movement, and it's chaotic, sudden disturbances, sudden varying in a velocities. So that we are calling as a turbulent flows, and these turbulent flows mainly used movement with mixing of fluid particles. So mainly these turbulent flow is used for mixing purpose, for mixing the chemical. So for mixing purpose or for heat exchange, we use the turbulent flows. So and these we discussed high velocity, low viscous nature for turbulent flows, and here this type of flow we see for larger diameter of the pipes. Larger diameter favors the turbulent flows, while the small diameter of the pipe favors the laminar flow. The increased energy loss due to the eddies and vortices, due to the movement of the particles, random movement. So there is a development of eddies in the flow. So that eddies are vortices creating the high energy loss. That due to that, there we are seeing the increased energy loss due to the eddies or vortices in the flow. And these examples of these turbulent flows are rapid river rapids and airflow over aircraft wings. Now, next differentiation is velocity profile. Next differentiation is velocity profile. Right, in differentiation, the velocity profile, the laminar flow has a well-defined path. So that's why we are saying the velocity distribution is in a parabolic way. right? In last class also we discussed, right? Here at the boundaries we are seeing the velocity is 0, right? At the velocity is 0, and we are seeing for laminar flow the velocity is maximum at the center, because due to this friction and logic resistance to the flow offered by the boundaries or offered by the wall of our solid, right? There we are seeing a velocity is 0, right? As we are moving away in diameter, we are seeing the less frictional effect. So as we move to the radius of the pipe, in that at radius we are seeing the velocity is maximum, right? This is for turbulent flows, the flow which is having the Reynolds number less than 2000. Now here is the turbulent flows. So turbulent flows is also same. At the boundaries the velocity is 0. At the boundaries the velocity is 0 due to the frictional resistance offered by the solidal wall. Right, as we move due to the zigzag nature, due to the high velocities, the turbulent flow profile is a flatter velocity profile and more uniform distribution. Here, the more uniform distribution, and we are seeing the flattened velocity profile. This is what a turbulent flow. For turbulent flow, which is having Reynolds number greater than 2000 up and maximum 2000, mean that is a 4000 Reynolds number turbulent flow. Right? Here the shear stress is maximum in turbulent flow near walls. Shear stress is maximum. Yes, now coming to the shear stress. The shear stress is maximum at the wall and minimum at the center of the wall. Here the maximum, the shear stress is 0, and at the wall the shear stress is maximum. Right? This is for shear stress. Right? uh, Comparison energy losses, yes, shear stress, as we said already discussed, the laminar flow having the low energy dissipation, that is low energy loss, because and having the low shear stress also, because all the particles are moving in their own path. That's why we are seeing less energy losses. In turbulent flows it is high energy loss due to the friction and due to the mixing of the particles from one to other in a zigzag manner, right? These practical implication in pipe flows and in machine efficiency. This practical application is. And here the laminar flow is the application of the laminar flow is for lubrication systems, blood flow in capillaries and microfluidics. Turbulent flow applications are mixing of chemicals in reactors. Turbulent flow mainly used for, and second is the cooling of electronic components, right? And third one is your aerodynamics in automobiles and aircrafts. These are the another differentiation of the application in laminar. It is blood flow in capillaries, lubrication system, and microfluidics. Right here in turbulent flows, here it is mainly used for the mixing purpose. Another is cooling of electronic components and also aerodynamics in automobiles and aircrafts. The experimental is a flow visualization technique for dye injection and PVI, wind tunnel testing, and computation methods, CFD simulation for flow analysis, and Navier-Stokes equation for turbulence model. Right? We are this Navier section. These two is for computational, that is a CFD, the computational fluid dynamics. Software is ANSYS. We can visualize the flow by using this software ANSYS CFD. In that we can visualize the flow by giving the respective parameters, all the values, all parameters, so that we can see the flow. And main the differential between those two flows are the laminar flow will move in a smooth path, and here the turbulent flow is a chaotic and a mixed flow, right? And here one more thing is this mainly used in aerodynamics and medical sciences, right? And here main the CFD and experimental for behavior of the flow in a circular pipe, right? Two methods. We can, by using these two methods, we can find the what type of flow is moving in a circular pipe. And if high velocity, low viscous nature, it is the turbulent. It is the flow. We can say that it has a turbulent flow. And if the flow is less, if the flow is moving with a low velocity, with a high viscous nature, then we call it as a laminar flow. The velocity profile for that laminar flow is a parabolic, and here is a uniformly distributed and flattened profile of the for the turbulent flows. Right? These are all the differentiations of a laminar and turbulent flows. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.